So, start the exercise session.
Yes, I mean, I guess the intention now was that I should try to talk you through some of the solutions or the ideas of the solutions that are on the exercise sheet. But you've all had a lot of time to try. So let's go. And so with the first exercise, I'm probably not going to say anything about it other than it's just a direct calculation. It's literally just using it with gamma sum matrix A, B, C, D. We had to find the action of gamma 1 tau as A tau plus B over C tau plus D. And you can simplify all of this to the right-hand side, and similarly you can compute the imaginary part of gamma tau as the right-hand side there. So it's just should be a straightforward calculation. So we should maybe go on to something slightly more interesting.
If I to rise your volume. No, that's not the same. It's not the same. Do you know how to change the volume?
So volume of speakers in here or volume of
the speakers?
Or should I just try to talk louder?
Yeah, that's a good algorithm. Missing other options.
Okay, so what I'd actually like to do, maybe first of all, is skip exercise 2 and go on to exercise 3 first of all, because I want to use exercise 3 to cheat a little bit at exercise 2. And exercise 3 is kind of this very important one about finding, explicitly giving the fundamental domain for SL2Z. So let's try that now. So the question is asking us to show that this nice picture that Danilo had on the slides or the tablet actually gives the fundamental domain for SL2Z. That was I. That's 1 plus root I over 2 minus 1 plus I root 3 over 2. And the idea is to show that every single point in the upper half plane, some random point tau, can be mapped under SL2Z into here, possibly to a point on the boundary where it gets some extra identification. I might actually grab. Okay, so the idea, first of all, is oh, right, so I should have done that. So the idea is we're going to use two particular matrices, the S and the T that were introduced. T being the translation, so 1101, which sends tau to tau plus 1, and S, which is 0, 1, minus 1, 0, which sends tau to minus 1 over tau. To take any arbitrary point up here and do a sequence of steps to move it into what we claim is the fundamental domain. Fundamental domain is script F. So step 1 is to take any tau and move it such that the The real part is between -1/2 and 1/2, and we can obviously do that with the translation by 1. So t to some power until the real part of tau is between -1/2 and 1/2, and that will land us somewhere in this whole green strip. And step 2 is, if tau is not already in the fundamental domain, then the absolute value of tau has to be less than 1. It's inside this circle.
Sorry, can't see you. The lowest factor of this sheet is not. Thank you. Now it's good.
So if tau is not already in this fundamental domain, then it's lying inside this, well, the intersection of this circle of absolute value less than 1 and whatever's inside this strip. So we have that tau would have absolute value less than 1. In this case, now take S tau, which was sending tau to -1/tau. You can check from the previous exercise that the imaginary part of -1/tau is going to be imaginary part of tau over absolute value of tau squared, is going to be strictly greater than the imaginary part of tau that we started with. So somehow we're going to be increasing the imaginary part by flipping with S. So now we have these two steps that can move something into the strip 0, 1, then flip it to get a bigger imaginary part. We keep repeating those until hopefully the algorithm terminates. And I say hopefully because this is something we do need to check. But for example, the idea here is that there would only be a finite number of points, there would only be a finitely many C and D such that C tau plus D has absolute value less than 1. So eventually we're going to hit a point where we aren't inside the unit circle and so have already hit something in the fundamental domain. And for example, to see this, you can just expand out that the absolute value of this, if I write tau is x plus I y, get something like requiring cx plus d squared plus cy squared is less than or equal to 1. I'm trying to scroll up with the but then just by doing silly approximation, if that is greater or equal to 0, we would have that c squared y squared is less than 1, which implies absolute value of c should be less than or equal to 1/y. And so for a fixed tau, this is going to mean there are finitely many choices for c that will land inside that circle. And then for each choice of C, you can plug back in and find there's only finitely many choices for D. And so now this would show that the algorithm actually finishes. And therefore you eventually land inside the fundamental domain or possibly on the boundary of it.
Maybe I'm being slow. Do we know for sure that applying sequences of S's and T's, we don't get the value we started with? value that we've already had.
Yeah, so the way I've set things up means that that should be impossible. So maybe I try to draw a slightly better diagram. We take some random point tau here, and just a half minus a half, and use first the translation t to move it in steps of 1, which is really not to scale here, so that it lands in here. Then with s, I can flip it so that the imaginary part is now strictly bigger than 1. Sorry, that's not quite what I want to say. If the imaginary part is less than 1, I can flip it again, but this might well land somewhere over here now. The point, but one is there's only finitely many C and D such that you get this imaginary part condition C tau plus D less than 1, which means we never get into a loop. So you end up doing something schematically like this.
So whenever you apply S, you always strictly increase the imaginary part.
So there's some way in which you can set it up to say that, yeah, as you do the sequence moves, the imaginary part will keep increasing, so you don't get into any loop. So schematically, you end up doing something like this. The picture's a bit blurry.
Thank you.
But then there's something else to check. I maybe want to say a word on what happens about identifications on the boundary. So obviously, if I take any point on the line minus a half, real part equals minus a half, and apply t to it, I'm just going to land on the other part of the boundary. So these 2 points really should be identified. Similarly, if I take some point down here and apply the map S to it, it's going to keep the absolute value equal to 1 and land somewhere over here. So there's another identification going on down here. But by setting up the cases and checking the details a bit more carefully, you can show that these are exactly the identifications that are going on. And therefore, every point in the upper half plane lands either in a unique point inside this fundamental domain, or on the boundary df with these indicated identifications. And somehow it's like a very vague idea. I'm not sure if it's worth doing this, but it's a very vague idea. You somehow want to check the possible conditions. And you end up reducing to checking certain cases where you solve all the solutions, C tau plus D, absolute value equal to 1. Come up with a list of cases to check. And for example, when C is equal to 0 in this case, you end up having to consider the matrix gamma, so 1 something naught 1, which when you want to check, when you want to see that it maps a point that's on the boundary of the fundamental domain into itself, it has to be the translation by +1 or -1. Slightly more tediously is checking what happens in the case C equals +-1, D equals +-1 or 0, where you have a few cases to consider, but they all end up mapping. It ends up being this identification down here. So then let's actually have a look at using this to prove the claim that SL2Z is generated by these maps S and T, the translation and the inversion. So writing that SL2Z is generated by these two matrices. So that is, we know from part A that any point in the upper half plane can be translated to something in the fundamental domain by these maps. So let's write the gamma prime to be the group generated by that, and you're trying to show that gamma prime is all of SL2Z. Now let's pick point tau in the fundamental domain, and how do I want to say this? And consider for any matrix in SL2Z the image of tau, which lands somewhere in the upper half plane. So gamma is just any arbitrary matrix ABCD in SL2Z. From part A, we know that we can find gamma prime in this subgroup generated by S and T, such that gamma prime maps this point gamma of tau back into the fundamental domain. So that is, I've taken some point in the fundamental domain, picked any random matrix I want to send it somewhere else in the upper half plane, and using the algorithm from part A, I've mapped it back into the fundamental domain, possibly to a different point. So the key idea here is it can't be a different point. So from part A, admittedly there is something of an extra step where one has to check there were no extra identifications. So one has that every point in the upper half plane is equivalent to a unique point tau in this fundamental domain, or for a point on the boundary. There's some steps you have to go through to check that carefully. This implies now that the combination gamma prime gamma tau has to be equal to tau. And therefore, since this identification is unique, we end up getting that gamma prime gamma has to be the identity. which implies the arbitrary matrix we started with has to be in this group generated by S and T. So this would then give us the conclusion that SL2Z is generated by the two matrices. On the next exercise sheet, there should be a question on, in fact, showing that a certain subgroup is generated freely, so there were no relations. And maybe I'll say more tomorrow about how that works in this case to show that actually there are no relations between the matrices S and T. But for this question, we didn't actually have to do anything more than that. So maybe we have a brief look at question 2. So the question is asking us to show that if we have some point that's fixed by matrix in SL2Z, it has to be, this point has to be equivalent to either I or this cube root of 1.
Sorry, we can't see it.
So let's take up to a matrix gamma, A, B, C, D as usual, and we're asking this matrix, is not the identity, to have a fixed point for this action. So we require that tau is equal to image under gamma of tau, so it's equal to A tau plus B over C tau plus D, which rearranging gives, say, C tau squared plus D tau minus A tau minus B equals 0. We can now assume C is not equal to 0, because if C was equal to 0, then the matrix would have to have the form, well, if C is 0, then AD minus BC determinant equal to 1 would force us to take 1, 1 on the diagonal, or maybe minus 1, they're equivalent rules, and something up here. So under this action, we'd be claiming that tau is equal to tau plus, let me write B there, tau is equal to tau plus B, where B is non-zero, because I started with a matrix that's not the identity, and that's obviously nonsense.
That is A tau plus B. Blind spot.
That one.
No, blind spot. So C tau squared equals plus D tau equals A tau plus.
And I wanted to take everything over to
Oh, sorry, is that
one side.
minus?
That's a minus sign. So up to usual sign errors, you should get something like that.
Right.
So now we just want to solve this quadratic equation for tau and see what happens. So actually, I might write it out neatly just for clarity's sake. So the equation is d tau squared plus d minus A tau minus B equals 0, which implies quadratic formula. the tau should be the following combination. Now, if we want this fixed point, this is the fixed point of this action of the matrix. If we want this fixed point to actually be a point somewhere in the upper half plane, the imaginary, well, there has to be an imaginary part. So this should be, it needs to be imaginary, i.e. the thing under it has to be less than 0. But by expanding this out, this should be equivalent to AD squared minus 4 using AD minus BC is equal to 1 by the fact we're taking the matrix in SL2Z. And so to require this is less than 0 means we want the trace of the matrix to be of absolute value less than 2. And so it has to be either minus 1, 0, or 1 because all the entries are integers. And so we can really just now go through the cases. So we take A plus D to be 0. If we take the trace to be 0, then we end up writing that tau is equal to the following, which should just go straight to the simplification. Should be equivalent. Tau should be tau in this case should be A plus I over C. Now this is where I want to cheat a little bit and say we already know that this point should be equivalent to something in the fundamental domain. So I can argue that C can't be too big, and therefore I can take C to be 1 essentially. So we end up taking C as 1 and suddenly by and so by the determinant being 1, we end up with A equal to 0 as well by mapping it into the fundamental domain. So modulo a few details, this point is the one that's equivalent under SL2Z to I. If you then look at the case where the trace A plus D is equal to plus or minus 1, well, just by sort of flipping the sign of everything, I can assume it's equal to 1. We get that the fixed point has to be of the form to A plus 1. So this is always using that AD minus BC is equal to 1, and A plus D is equal to 1 in this case. Plugging back into the solution we had before, we'll just take this. And so you end up being giving the point 1 plus I 3 over 2 all over C. And by similar sort of cheating as before, and assume that C is equal to 1, leads to A being 0 or minus 1, which we can then relate with this translation. So this is the point that's equivalent to 1 plus I root 3, 1 plus I root 3 over 2 as the other fixed point. As I say, there's a little bit of cheating because I'm already assuming I know that everything can be mapped into the fundamental domain. You can probably do it more directly by checking some cases, but then it gives you an indication of how to do that question. I'm also worried about running far too much into lunch, so when you're ready for me to stop, just shout, please.
Maybe 5 more minutes.
A moment.
5 more minutes.
I can do that. So then maybe have a look at exercise 4. This is where I sort of want to show that one periodic holomorphic function can actually be written as a Fourier series, and there's sort of 2 ways to approach this. Maybe I go first to sort of this slick way where it essentially drops out as immediately true. I want to show that this one periodic holomorphic function on your graph plane has a Fourier series of the form ANQ to the n, summing over all integers. And the point here really is that this coefficient is constant. Because in one approach, you can very quickly see that it has a Fourier series, but you have some dependence on the imaginary part, and the idea is to show that that actually doesn't have a dependency. So I'll come back to that in a moment. Perhaps the slick way is to consider writing that q is e to the 2 pi I tau. So this will map a strip of size 1 like this into the function unit disk. So now we can take the function which we know is one periodic and use this to define related function of q just by the function on this continuum disk is going to be the value, the corresponding value in the strip. So you could write down versus something like 1 over I log q, and then argue that well find this. It's all the function is periodic, so it doesn't matter if you add an extra 2i pi when you go around what is a multi-valued function. So now the point is F holomorphic on the upper half plane means that in this picture, the function should have a Laurent series about the point 0. Which then immediately gives this maybe the Fourier expansion. And then you automatically got the coefficients being constant just because there's a convex function that's the Laurent series will have constant coefficients. No dependence on real or imaginary parts there, everything is bundled into the Q. The slightly more direct and I think I'd say more down to earth way. So that since the function is one periodic, we know that it has to have a Fourier expansion of the form minus infinity to infinity, some coefficient which depends on the imaginary part, that's the one periodicity is in the real part. And then we want to argue by the homomorphicity that this dependence on the imaginary part just has to drop out. And for this, we can just use the Cauchy-Riemann equations, say the function is holomorphic, so it has to satisfy those, see what that gives for the coefficients. And maybe the nicest form to write them here is this way with the sort of derivative with respect to z bar, if you want to define it as dx plus I've changed from uv to xy. Change back. To argue that the Cauchy-Riemann equations would say that this combination of partial derivatives has to be 0. And if you compute what this is, what this tells you about the coefficients Bn of v, you will get hopefully that that's something like Bn of y plus Bn prime of y has to be 0. Which tells you by just solving a differential equation that Bn of y has to be some constant times e to the minus 2 pi I n y. Which if we then plug back into here will give us exactly the form we want. So tell you that f of u plus iv is the sum of the following form, some constant e to the minus 2 pi I n y. Sorry, there's a sorry, that should be the extra I here. The I here should eliminate with the I here and not be in the differential equation. And then this bit you just rewrite as e to the 2 pi x plus I y, which was tau. And then this is q to the n. Gives you another way of seeing that this one periodic function has to have the claimed Fourier series. Now, in the interest of not eating too much into lunch, could stop here.
We can discuss the problem over lunch.
We can either do that or I can maybe say something about it tomorrow in the exercises.